We're starting with the basics. Motion is simply when something changes its position, and a force is what makes that change happen. Think about a game of tug of war. The pull on the rope is a force. If that pull is strong enough, it changes the motion of the other team. Forces are the invisible pushes and pulls that control every movement around us. Centuries ago, Sir Isaac Newton gave us the rule book for all motion in the universe, his 3 laws of motion. These laws are the bedrock of physics. The first law talks about inertia, and the third law talks about equal and opposite reactions. But today, we are going straight to the most useful law for understanding cause and effect, Newton's second law of motion. Before we get to the law itself, we need to understand a key concept, acceleration. Acceleration is what happens when a force changes an object's velocity. Remember, velocity is both speed and direction. So, an object accelerates if it speeds up, like a car when the driver steps on the gas, or if it slows down, like when they hit the brakes. Even turning a corner is acceleration, because the direction changes. Newton's second law is simple but profound. It tells us exactly how much an object will accelerate when a force is applied. It says that the acceleration of an object depends on 2 things, the force applied to it and the object's mass. In plain English, if you want something to move quickly, you need to push it hard. We can write the second law as a powerful mathematical equation. Force equals mass times acceleration, or F equals m times a. In physics, we measure force in a unit called the Newton, N, named after Sir Isaac himself. Mass is measured in kilograms, and acceleration is measured in meters per second squared. This one little equation allows us to calculate any of the 3 variables if we know the other 2. Let's look at the first part of the law, the relationship between force and acceleration. Imagine you're pushing an empty shopping cart. If you push it gently, it accelerates slowly. If you push it really hard, applying more force, it accelerates quickly. When the mass stays the same, increasing the force always results in a proportional increase in acceleration. This is called a direct relationship. Here's a simple calculation to show that direct relationship. If you push a 10-kilogram block with a force of 5 newtons, it accelerates at 0.5 meters per second squared. Now, if you double your effort and push with 10 newtons of force, the acceleration doubles to 1.0 meters per second squared. Keep the mass constant, and acceleration follows force directly. Now for the second part, the relationship between mass and acceleration. This one is an inverse relationship. Imagine applying the same amount of force, say your maximum push, to a soccer ball and then to a bowling ball. The soccer ball, with its low mass, will take off quickly. The bowling ball, with its high mass, will barely budge. More mass means less acceleration for the same force. Let's see the numbers for the inverse relationship. You apply a constant force of 10 newtons to 2 objects. Object A has a mass of 5 kilograms, so it accelerates at 2 meters per second squared. Object B has double the mass, 10 kilograms. Its acceleration is only 1 meter per second squared. Double the mass, and you get half the acceleration. In the real world, an object is rarely acted upon by just one force. If you push a desk, you have your push, but you also have friction working against you. The only force that matters for calculating acceleration is the net force. The net force is the total overall push or pull that remains after all forces are added up. The net force concept is key. If all the forces on an object are balanced, they cancel each other out, and the net force is 0 newtons. According to the second law, if F equals 0, then A must also be 0. The object won't accelerate. It will either stay still or keep moving at a constant speed. Only when the forces are unbalanced and the net force is not zero will the object accelerate in the direction of that net force. Let's use the formula F equals m times a to solve for force. Say you have a 2-kilogram toy car and you want it to accelerate at 5 meters per second squared. How much force do you need? You simply multiply the mass by the acceleration. 2 kilograms times 5 meters per second squared. The answer is 10 newtons of force. What if you know the force and the mass, but need to find the acceleration? We rearrange the formula to A equals F divided by m. Imagine you apply a 50 newton force to a 10 kilogram suitcase. You divide 50 newtons by 10 kilograms. The result is 5 meters per second squared. That's how quickly the suitcase will speed up. You can also use the law to find the mass. We rearrange the formula again to m equals F divided by a. Suppose a 10 newton force causes a ball to accelerate quickly at 20 meters per second squared. We divide 10 newtons by 20 meters per second squared. The mass of the ball is 1 over 2 kilogram, or 0.5 kilogram. It must be a very light ball. Two crucial real-world forces affect acceleration. The first is friction, which is the force that resists motion when two surfaces rub together. If you push a block across a rough carpet, the friction is working against your push. This reduces your net force, so the block accelerates less than it would on a smooth, slippery floor. The second essential force is gravity. Gravity is a force of attraction, pulling all objects with mass toward each other. On Earth, the pull of gravity is what causes objects to fall, and is also what gives an object its weight. When you throw a ball, the net force is your initial push, combined with the constant pull of gravity acting on the ball's mass. Newton's second law is everywhere in sports. When a baseball player hits a home run, they are applying a huge force to the ball's relatively small mass, resulting in massive acceleration. Conversely, when a shot putter throws a very heavy metal ball, they have to apply a much greater force to achieve even a modest amount of acceleration compared to a tennis ball. A unit of force, the Newton, is perfectly defined by the second law. 1 Newton is the exact amount of force needed to make a 1 kilogram mass accelerate at a rate of 1 meter per second squared. So, 1 Newton is mathematically equal to 1 kilogram multiplied by meter per second squared. These units are intertwined thanks to Newton's second law. Let's summarize the big ideas for the second law. Remember the formula, F equals m times a. Force and acceleration are directly related. Push harder, speed up faster. Mass and acceleration are inversely related. A heavier object is harder to accelerate. And finally, always remember that only the net force acting on the object causes the change in motion.